Chat, just let me know. Are you always use or leave it in 14? Or you can't see me. Wait a minute. There, that's me. I always leave it in 14 if music is too loud, just let me know. Or if it's too low, also just let me know. Cool. We are online. StreamYard changed a bit. Wait a minute. Can I do this? Yeah, that's better. Cool. Hey everyone. Welcome to Global Hack Week, AI and Machine Learning Week. So glad for you to be joining me today for building a neural network from scratch. I know it sounds intimidating. It kind of is at first, but when you get the idea, it becomes just super easy. If you could please, what are my notes? Here. If you could please check in here. That should be good. Cool. Awesome. Yeah, so let's get started. I have a presentation. Then we're going to go to Colab. We're going to program everything in Google Colab. So you don't need to download anything. Everything in Google Colab, okay? Cool. So can I do this? Yes, there we go. I kind of don't like when it's rounded, when it's not rounded. Wait a minute, how can I do this? Maximize. Yeah, I don't know. I usually I'm used to having me in a circle instead of a square. But yeah, sometimes it happens. StreamYard just updates and you have to change the whole things. Okay, let's slideshow this, okay? Cool. So, hello again. Welcome to my stream, Intro to Neural Networks with, let's say Intro to Neural Networks. If we have time, we'll go to TensorFlow, okay? Ideally, we should have time for TensorFlow, but let's see. My name is Charbel. People call me Bully. You can call me by name or nickname. I'm a robotics and telecommunications engineer at work at an Australian startup specializing in drones, and also we are building a device that helps visually impaired people. So computer vision 100%. We have to make that device guide people and explain to them if there is a hazard. If they're looking for, I don't know, for milk, then it has to be smart enough to guide their hand to reach the milk and so on. I'm also at MLH. I'm the program coordinator at the MLH Fellowship. So if you have a question about the MLH Fellowship, make sure to send me a Discord message, okay? Cool, and by the way, I'm 24, so yes, that's me. Awesome. So I love AI, okay? AI is probably something that I fell in love back in the day when I was like 19, 20. I didn't know anything about AI. I was like, oh, that sounds cool. You can program it. And I learned TensorFlow. The only bad thing of kind of leaping directly to TensorFlow, it's that lots of the basics, I wasn't sure what I was doing. So for example, Colab. Oh yeah, for sure. Colab is the best thing. You have GPUs, CPUs, DPUs. It's really good. So the bad thing about jumping or making the leap to TensorFlow without kind of knowing or getting to know the math behind a neural network was that a bunch of errors that I got was I didn't know what to do. So back in the day, we didn't have ChatGPT. I feel like an old man now. But you know, you just copy paste the whole thing into Google, and it gave you someone kind of asked that in Stack Overflow, and I kind of just learned about it. But then I took a course in Coursera from Andrew NG, one of the best people in AI today. I learned a bunch of things. A bunch of other things I didn't learn them because it was so complicated, okay? So let's go step by step with me, okay? I don't want you to fall into that, let's call it unknowledge trap. So let's go step by step, okay? A lot of math, okay? A lot of math, but very friendly, okay? So I'll do it as friendly as I can, okay? So let's go with the presentation first, okay? Yeah, accessibility devices are really cool, especially when they work. If they don't work, Nah. And ours is kind of working, but the AI part is on me. So it's like complicated sometimes. It's fine. I have fun, and that's the important part. Will it work? I hope so. Cool. Okay, what is AI? So AI stands for artificial intelligence. We all know that, which is a branch of computer science focused on creating systems or machines that can perform tasks that usually require human intelligence. Okay, the gist of it is we make computers smart. These tasks might include understanding language, recognizing images or sounds, making decisions, and learning from data. Okay, and you can see this here. You can see a circle, okay, which is the usual map of AI. AI is englobes or is everything that has to do with a machine making decisions. Okay, from a simple chess game to something like a Tesla just driving itself. Okay, that's AI. If we go into terms more scientific, you can see that we have machine learning and deep learning. Machine learning stands for a machine that takes data and learns from it. It's not only a neural network. It goes or it can be you can have equations. I just forgot the name. You just do lines. Wait a minute, how was it? Oh yeah, linear regression. Yep. So linear regression falls into machine learning. It's not a neural network. It's just you're just learning and kind of tweaking a line so you get the output that you want. Deep learning is only focused on neurons. Okay, so machine learning doesn't have neurons. Deep learning does. Okay, but artificial intelligence is basically everything. Okay, it's the common phrase that we use. Hey, it's AI. Okay, cool. So what is a neural network? Okay, what the heck is it? A neural network is a type of AI designed to work like a human brain. Uh, I would say not a human brain only. I would say a biological brain of creatures from this planet. Okay, it's made up of layers that we call neurons, which are simple units that process information. Okay, and we'll dive into that in a bit. These neurons are connected together and work as a network. Okay, that's why you call it neural network, because it's a bunch of neurons talking to each other, sending mathematical data, doing math basically. So from the input, we get the output desired. Okay, so is this a dog or a cat? It's a cat. Okay, and that's what the neural network does. Okay, for example, imagine trying to teach a computer to recognize a picture of a dog. Then you have to break down the images into pixels. Okay, that's what the basic unit of an image is in a computer. And then these numbers, which pixels are numbers, are sent through a network layer by layer. Each neuron adjusts how much it pays attention, you can see it that way, to the information. Yep. And at the end, the network gives an output of yes or no. Okay. If you have a more complex neural network, then output is not yes or no. It might be this, and that. Okay. And it doesn't give it to you friendly. It just gives you numbers. And you have to understand what those numbers are. Okay. This is how it looks. Okay. You have an input, you have the hidden, and you have the outputs here. You can see inside of each neuron, you have an activation function, and you get the numbers from the outside. You activate those numbers with an equation, and then you get the output. And you connect it to other layers to get more accurate things. Okay. So far, so good. Okay, I know it's a lot. I know it doesn't make sense. You're like, yeah, what the heck is going on? Bear with me. Okay, bear with me. We're going to dive into the math, but I hope everything's okay. If not, chat, as always, let me know. And I'll just pause and kind of try to answer to your questions, okay? What is an activation function? Okay, so each neuron inside of it has an activation function. It's a key part of the neural network. It decides whether the network should be activated or not. Okay, so if we don't activate neurons, the input is the same as the output. You're just giving it some numbers and that's it. You're not deciding. Okay, So we don't have linearity in our neural networks. We give it activation functions. We have in this example we have two. We have sigmoid, which is a number from 0 to 1, okay, and we have ReLU, rectified linear unit, okay, and you can see here the equations of them: 1/1 plus e to the minus z, and then this is either ReLU just takes the max number or 0, okay. That's simply it. Cool. We have a lot of types of neural networks. I'm going to kind of just go fast, okay, because we're running out of time. Okay, so we have a feed-forward neural network is the one that just goes forward. It doesn't go backwards, so it doesn't kind of learn. We don't tweak based on the error. We just predict. Okay, cool. We have the CNNs, which are convolutional neural networks. They are specialized for images and visual data. Okay. For a second, previous slide, you mean the slide over here? Yes, I could. Maybe I should do this. Wait a minute. Share. Yep, restricted. Copy link. Yeah, that's fine. I can share the presentation here. Cool. Okay, so where were we? We have CNNs. Okay, they're made for images. Okay, so these convolutional neural networks read images, parse images, and they can tell you what it is. Okay. Oh, wait a minute. There we go. Cool. Now we have. You don't have access. Wait a minute. What? Share. Oh, sorry. Yeah. Give me a second. That should be it. Yep, cool. Should see it now. Yeah, I saw it. Just try the new link. Should be all good. Cool, awesome. So we have recurrent neural networks. These are for sequential data. Sequential data is awesome. You're welcome. Sequential data is the data that has to do with the previous one. So videos, okay? A video, one frame has to do with the other one. Yes, so it's linked, so it kind of remembers. Okay, you are welcome. We have LSTMs, which are long short-term memory. Okay, these are recurrent neural networks for better remembering information over long times. Okay, we have GANs, generative adversarial networks. These are two networks, one that generates and the other one that discriminates. It sounds not good, but it's basically one that generates and the other one corrects. So that's how they do it. And yeah, that's the whole presentation. Okay, cool. Now I wanted to go fast because we're going to look at a lot of math. Okay, cool. Can I get rid of this? No, I can't. Can I? Yeah, there we go. Cool. Okay, so by the way, you can find this and everything that I'm going to show in my GitHub. Okay, I'll share the link in a second. Okay, it's this repo, and then we have to go to AI. This one. Okay, so it's this PDF. Okay, you can see everything that I'll write. It's in here. Okay, so don't worry if you don't get it to write it down or take a screenshot. It's already here. Okay. It's right there. Cool. And the codes here are everything here. Okay. The templates, everything's here. Okay. Cool. So let's see. Oh yeah, a note. Cool. So just let me know if I need to zoom in. I'll zoom in just because. But yeah. Cool. Okay. So first of all, this whole intro to neural network stream, I'm basing this stream on Samson Zhang's video. Okay, he dives into the math, and I took the math, and I'll also explain it to you. But yeah, shout out to Samson Zhang. Okay, if you watch the video, it should be here. Okay, and this code with the video is right here. Okay, it's this one. Cool. So let's start. Okay, we are going to feed. That's the first project. We're going to feed a neural network with images of numbers. The neural network has to be able to understand the numbers, correct itself, train, and give us the correct output after a certain amount of training. Okay, so let's dive into the theory first, and then we'll go to the code. Okay, so we'll talk about lots of things. First of all, part one is the inputs, okay? This is probably the most important part of building a neural network project. If you don't understand what the neural network will receive, you won't be able to train it. It might be YOLO, which stands for you only look once, a neural network that looks at images and classifies things inside of the images. It might be the best neural network. If you don't have your inputs correct, you won't be able to train it. Okay, so inputs part, very, very important. We have something called M. M stands for number of images. Okay, should I zoom in? I think it's okay, but just let me know if I should zoom in. M stands for the number of images. Okay, so our whole data set is M. Okay, we have something else called classes. Okay, classes are every possible way that you can segment the images. Okay, so let's call it like number of possible classification. There we go. Is that good? Yeah, cool. Okay, so those are the classes. In our case, we have 10 classes. Okay, from 0 to 9. Okay, 0 to 9 are the numbers that we're going to feed the neural network. Okay, those are going to be numbers handwritten. 0, 1, 3, 2, 5, 0, 5, up until 9. Okay, no more than that. Okay, so we have 10 classes. Cool. Now, we have our image. Okay, so our image is going to be a square of 28 by 28 pixels. Okay, so far so good. That's our image. Okay, how do I know that? Because I know the data set. That's why I know that the images are 28 by 28. Images are usually not 28 by 28. Okay, usually they are like 256 by 256, which is a usual number used for neural networks. We can have, I don't know, 500 pixels by 500, 500 by 400. It's up to the image. Okay, cool. Now, we can see that the total amount of pixels is actually 784. Okay, remember this number. That number will be equal to your first layer of neural network. Okay, so we have to have 784 neurons, one per pixel. Okay, so it connects like that and it activates one per pixel, and then we can just reduce it, feed forwarding only the numbers. Okay, sound good? Cool. Now, I know it's a lot of things. Bear with me, okay? I promise you there'll be code. Just bear with me. Okay, the X is our data set. Okay. You can see that our data set kind of looks, you'll be able to see it in a second, looks like this. Okay, like this. So you see that the data set is a list of images, and each image is a list. You can see it's like a list of lists. Okay, speaking in Python language is a list of lists. Okay, that's not good for us. Okay, we need to transform this into something like this. Okay, so we need to kind of rotate it 90 degrees. And in math, this is called transpose. Okay, so we need to transpose the images. Okay, we have to do math in matrix math. That's why we have to transpose it. Okay, we have to have dot products. If you don't transpose it, you'll get an error. Okay, cool. Now, that's our input. Okay, we know it's an image of 784 total pixels. We know it has 10 classes. Oh yeah, that's because you do dot products and you want each neuron to be linked to each pixel. If you don't rotate it, then when you do the dot product later on, it won't make sense to the neural network. Okay, that's why. Good question though. Cool. We know that this is what we want. Okay. Now, what about our brain? Okay. So we do part 2, the neural network. Okay. Can you see that part? Yeah. Oh, probably. There we go. We need to design, since we're doing it from scratch, we need to know the number of neurons. If you don't get it correctly, you'll get an error. Okay. That's how math is. Okay. So we got X amount of, we don't know how many right now, neurons like this. Yeah. Imagine they're all interconnected to another layer. And then, there we go, another layer. And then we'll get something like this. If you see y hat is always our prediction, okay? Is what the neural network thinks it is, okay? If we put a dog as an input and the neural network says, hey, it's a cat, it's a bad prediction, but it's still y hat, okay? We know that our first layer is going to be the input. Is going to have 784. And this is, remember, the number of pixels. Okay, we'll give it more or less. It'll be an error. Okay, now the first hidden layer is going to be layer number 1. And layer number 1 is going to have 10 neurons. Why? Well, basically, why not? Okay, you can choose from this point forward, you can choose the number of neurons based on what you think. Okay, that's the kind of the art of the neural network design, is that you can choose how many neurons it has, how many layers, what kind of layers it has. Okay, that's up to you. Okay, cool. And then layer 2 is going to have 10 as well. And this is important. Okay, first and last layers have to make sense. Okay, we have to have 10 neurons here in the last one because we have 10 classes. Yep. So far so good. We have to have an X, or like number of pixels as input, number of classes as output. The middle of it, the inside layers, it doesn't make, like, it's not important. You can have as many layers and as many neurons as you want, as long as they're all interconnected. But the input and the output should make sense. Okay, sound good? Everything good? If we have 11, that wouldn't make sense because we don't have 11 classes. Okay, cool. So that's that. Interestingly enough, if you have, let's put it like in a cloud here. Like if you have 2 classes, then you should only have 1 output neural network. I'm sorry, 1 output neuron. Okay, why is this? Because if you remember, we have a function called sigmoid. Okay, it's kind of like this. Goes from 0 to 1. This can give you a number from 0 to 1, and both of them it's a yes or no. Yep. So we can say yes cat, no cat. If it's not a cat, it's a dog. Okay. That's kind of the logic of it. Okay. So if we have 2 classes, just 1 neuron. Okay. If we have 3 classes, we need 3 neurons. Okay. Kind of confusing at first, but you get it once you understand this equation. Okay. Cool. Now, okay, brace yourselves. We're getting into deep math now. Okay, we need to do 2 things. We need to feed forward and back prop. Okay, feed forward, remember, is to predict an image. Okay, basically to do the math and say it's a 1, it's a 9, it's a 5. And back propagation, it's taking the output and saying, hey, we know the answer. Your answer was not correct. We get an error, and that error moves the weights so that the neural network kind of tweaks itself. So whenever we pass that number again, it should activate different neurons more related to that number. Okay, it's a bit confusing. We'll see it in a second. Okay, cool. So let's see. Should I? Maybe I'll take a lot of time into writing this down. I'll just do the easy thing. Okay, I'll share it here. Okay, yeah, because I'll take a lot of time, and it's like half an hour past. Let's just read it out. Okay, cool. So far so good. We have our neurons, layer 1, layer 2, and again, binary classification has 1 neuron. Okay, cool. Now we have. Let me do. Can I? Probably should open the whole thing. Wait a minute. So it's easier for you to see. And there you go. That's better. Cool. So for the forward propagation, we have to do math. Okay. Basically, we input an image to get a prediction out of it, and we don't learn. Okay. We are just predicting. Okay. The W stands for weights. Weights are numbers, the output numbers of the equations. A bias is an outside number that just makes sure that we don't get linear activations. Okay, so that we don't get untouched numbers, so that we always get weird numbers. Okay, just imagine the bias is someone that is kind of pushing the numbers so that they don't get the same number each time. Okay, the input layer, it's here. You can see we are saying it's A0, and it's only X, which is, I think I got it wrong here. It should be 784 pixels, okay? And that's why we have, oh, I'm sorry, it's 284 times M, okay? Which is 700, this one, okay? This number right here, okay? Which is each pixel of the image, okay? We pass, you can see I marked them with colors, so you can kind of see how connected they are. We pass this number right here, and we will multiply the weights, which at first are random numbers from 0 to 1, okay? Multiply it by this number right here, plus the bias. And we get first neuron, okay? It's not activated. It just multiplied by weights plus a bias, and this is just linearity. Okay, it doesn't do anything. We need to activate it. What we do is the next step is we pass Z1 to the activation function, and our activation function in layer 1 is going to be ReLU, which is this one over here. Okay, you can see it's just max between 0 and the number that we give it. Okay. Now we take A1, you can see the orange, pass it to layer 2, and say, okay, Z2 is W2, which is the weights that, again, the weights are the numbers that you tweak so that the neural network learns based on the error, okay? Times the previous activated layer plus bias, okay? It's the same thing. We do the same thing here and here, okay? And we have to activate it, okay? And now remember, layer 2 is the one that's going to give us the prediction. we have to activate this with softmax. Softmax gives you a percentage between 0 and 1 of the 10 classes. Okay, so if the neural network says, hey, I'm pretty sure, I'm 90% sure it's a 0, I'm 5% sure it's a 1, and I'm 5% sure it's a 9. So it'll be 90, 0, 0, 0, 5, 0, 0, 0, 5. Okay, that's softmax. So we have to get the maximum number that softmax gives us. Okay, cool. So far, so good. No questions. I know it's a lot. I know it's a lot of math. Okay, so far, so good. Okay, you can see the connections with the colors. Okay, that's why I colored them, so it's easier to understand. Okay, cool. Now, we're just predicting, we're not learning. Let's learn. Learning is from the prediction and the ground truth that we know, because each prediction, each image that will feed will just keep the right answer. We'll compare it later and say, hey, a neural network said it was a 2, but it was a 3. Let's get the error of that and then change the whole thing. Okay? We calculate the error and adapt the weights. We don't adapt the equations, we adapt the weights. Okay? So you can see back prop layer 2. We go from back to front. Okay? I put like a differential here, so you can see it's like the error, okay, like the change that we're going to do. DZ2 equals the output minus the ground truth. Okay, so we get the error. Okay, the error, or let's say that the output is going to be looked like this. This is one hot encoded. It means we have 10 classes, we have 10 numbers. As softmax outputs probabilities, we know that in 0, the first one should be 0, the second one should be 1, third one should be 2, so on, okay? We might get, that's a methodology of programming, or is it algebra and numbers theory? Or what do you remind us? Okay, this is calculus, okay? We're doing, it's not algebra per se, we're just getting the equations to program them later, okay? But yeah, it's sir, which course? That's a very, very, very good question. I'm not sure. So I'm pretty sure there's like an intro to AI course, but I'm not sure. Like I'm not sure what like the name of the course that should be given, but it's basically an intro to neural networks. You can see it that way. But yeah, I can share links later. But yeah, I if you go to my GitHub, you can see here in Intro to Neural Network Part 1, you can see that the first line is a link to Samson Zhang's video that I'm basing this stream on. Okay, but yeah, cool. Okay, yeah, it's like math. Okay, it's like I don't think it's number theory. It's just I'm pretty sure it more relates to calculus. Okay. We differentiate some things here and there. Okay, cool. So we get the error. Then from the error we get DZ2. DZ2 is here. You can see. So we get 1 over m. Remember, m is our data set over DZ2, or DZ2 over m times A1, but transposed. Do you see that? A1 is this part over here. It's layer number 1. Okay. Not input layer, but layer number 1, okay? Don't forget to transpose it. If not, you're gonna get an error, okay? Yeah, so far, I think we'll differentiate here, okay? In this part over here. You can see it as 90% linear algebra, 10% calculus. Yeah, we'll have to do math when you use coding. Yes, but not like this. It's an easier way to do it, okay? Cool. Now, we get DW2, which are the weights. We are changing the weights based on the error. Okay, we do the same thing for layer 1. We get DZ2. Okay, we have to activate it by the activation function, but there's oh yeah, for sure. Oh yeah, for sure. Check this out. Oh yeah, this is easy. Like this is easy. Check a very difficult neural network, and this is like the easiest thing you can find. if you understand it, it's fun. It's fun actually. But okay, so we have the weights transposed times dz2, which is the back propagation of layer 2, times, this is a dot product of the activation function. You can see here there's a comma, or there's a thingy here. This is the linear, or I'm sorry, the activation function derived, or how do you say this in English? Derivation, like you derive the activation function. So you kind of unactivate, if it makes sense. Okay. You get dz1, we get the weights. We do the same thing as with dz2. Okay, here. And you change the bias to, and then you just have to update the whole thing. And voila. Okay, you can see here there's alpha. Alpha is our learning rate. Okay, is the size of steps to achieve a low error. Okay, so imagine that you're looking for, okay, let's see here. Okay, these squares right here. Let's say that you're here. Water is here, or water is 2 steps ahead, but you're doing a 3-step jump. So you will never reach water, right? You will just jump around it, but never reach it. That's alpha. Okay, we can have, if you say, hey, we can have alpha very, very large to learn faster. Well, yeah, but you'll never achieve a good result because you're never touching the result. You're either changing the number super fast and it doesn't tweak little by little. If alpha is too small, you just take too much time. Okay, so we have to adjust alpha. Okay, cool. It's a lot. Let's look at it in code. Okay, so let me get my cheat sheet real quick. Open collab. Okay, in the meantime, I'll just get this. Get some water, please, because this is a lot. I have coffee, by the way, but yeah. Okay, so there we go. Here it is. Okay, my iPad is kind of slow. I have to change it though. I just don't want to buy a new iPad. I don't know. I'm not using it anymore. I just use it for streaming. But yeah. Okay. So by the way, I have cats here. So say hi to my cats. Okay. New network. New notebook. Okay. Cool. So we need a lot of things. Okay. By the way, maybe the easiest thing. No, let's leave it like this. Okay. It's fine. It's fine. Okay. So first line of code, or first cell. Okay. By the way, if you're not familiar with Google Colab, real quick tour. Should I upload shorts? I don't know. I don't have a channel. Like, this is MLH's channel. I was thinking I can do my own channel too. I'm not sure. I'll think about it. In the meantime, you can see here, this one's important. Okay, this folder. You have here your folder. You can upload things. Okay. What else? You can, if you hover under your cells or over your cells, you can add either code or text. Okay. This is to get rid of your cells. Okay. Cool. So we'll import pi as in p, import panda spd, and import matplotlib.pyplot as plt. If you're using Colab, you might get like the AI that finishes your code, or like auto completes your code. I hate it, so that's why you don't see it with me. Okay. Cool. How did I run this? You see here's a green tick. It means it ran without error. Okay. How did I run it without clicking here? If you do Control Enter, it runs. Okay. Nope, it's MLH's channel. Cool. So we have to do something first. Okay, we have to get our inputs. Go to Kaggle, and then Kaggle mnist dataset. Okay, this is the dataset that we're going to use. It's a very famous dataset. It's called the mnist dataset. You can see that the numbers look like this. Okay. Of sorting out and system of equations using Cramer method. Ooh. Alex, you just asked a question that I'm not sure how to answer. Okay, of course I have no right to disrupt. Don't worry, don't worry. But how do you like the idea of sorting out n systems of equations using Cramer? Oh my God, it's been a while since I've heard about Cramer. Um, let me just let's see if I remember real quickly. I'm not sure. Oh yeah. Mm. Yep, I don't remember Cramer. Yeah, I remember this. Doing it, I don't remember. Yeah. Text me on Discord, and maybe later we can talk about it. Okay, but I don't remember Cramer. It's been a while. Okay, this wasn't linear algebra. This was like there was a class called. I remember I learned Fourier there. Um, I'm not sure, but yeah, just text me later, Alex. Here's my Discord. But yeah, I'm sorry, I can't answer it right now. I just forgot about Kramer's rule. Okay. Cool. Shoot. Cancel. There. Okay, so this is how the MNIST looks. Okay. Now, we don't have to download it. Please sign in to Kaggle. I'll sign in with Google. Cool. If you go to if you don't have a profile picture, you'll see a duck. Go to your duck settings, and then you have here. Where is it? It's API tokens. Okay. Click on generate new token. Okay, I have my token, so no worries. I'll generate a new one just in case. Generate. When you click on generate, you click here, copy this. You can't see it later, so save it. Okay, close, and then I'll just put it here. Okay. By the way, no, we have to download it. Should we? Wait a minute. What? Wait a minute. You had to download it. How do you download your? Wait a minute. I see a question there. It should download automatically a JSON file. Yeah, that's funny. Wait a minute. Because what I have to do is JSON. Yeah, it's a token. Expire token. Nope. Oh, wait a minute. It has to be a legacy API. I think. Oh, curious. My bad. Okay. You click on create legacy API. Okay. Continue, and it downloads Kaggle JSON. Okay. I had one, so that's why it says one. Okay. But yeah. Happy holidays. Let everything work out. Oh, thanks so much. Yeah. Just let me know, Alex, on Discord. Okay. I'll try to help. I used this dataset during Cloud Week. Awesome. It's a very, very, very usual dataset. Can you briefly recap the section before moving on? Just got here. Okay, cool. So we are trying to. You can look into my GitHub. Okay, again, here's the link. Yeah, you can report it directly. Yep. But yeah, here I explain a little bit of the math behind the neural network. Okay. I won't explain it again. Just we are creating a neural network. The input is MNIST dataset. The output is hopefully the neural network understanding MNIST dataset. Okay, that's what we're going to do. Can you? Really? Really? Can you do it without the API key? I've always done it with API key. Well, let's do it with API key. But if you can send like a link to a tutorial of how to do it without API key, that'd be cool. Okay, no API key here. Cool, awesome. So upload your Kaggle JSON. Okay. Everything that you upload is going to be erased once you close the session. Okay. So everything here, if you want to keep, either save it in Drive or in your computer. Okay. Cool. So if you put an exclamation point before code, it means you're writing bash. Okay. Cool. Don't you need the API key even though you're doing that? You sure? I can copy paste the whole thing, but what are you going to collapse? Sorry, I don't use it. No worries, no worries. I think you need it for specific. Not in Kaggle, really? Wouldn't this work only for Kaggle notebooks? I'm not sure. I think it sounds familiar. I think I've seen that code before, but I think it asks you for your API key that you have to put later. I'm not sure. But yeah, sounds good. Didn't know that you didn't need it. Okay, cool. So we upload it again. Okay, so go into Kaggle, scroll down. Okay, go into settings here. Scroll down and find legacy API credentials. Okay, once you have that, click on here. Okay, I can't do it because I have already issued one. Create here, and it'll download something like kaggle.json. I have one, so that's why you see like here one. Okay. Not in Kaggle. Hugging Face you do, and I use Colab. Oh, I didn't know. Thanks, Mandy. I didn't know about that. It's easier because you don't have to import kaggle.json each time. But yeah, thank you for sharing. Okay, cool. So a funky capybara. Here you have your Kaggle. Okay, go to your Google Colab. Click on this thingy over here, or click on the folder. Click on the arrow, upper arrow, and then kaggle.json. Click on kaggle.json here. It won't because it's already there. But yeah, it should upload it. Okay, cool. Now that we have it, exclamation point for bash. Make dir stands for make directory. We want to make something called Kaggle. I don't know how to use this thingy. Just in case you don't, it's that thing over there. Okay. Squiggly line slash dot Kaggle. Okay. Then under it, CP stands for copy. Okay. So copy Kaggle.json. In my case, I'll just rename it because it'll. There we go. That's it here. Kaggle.json, where we want to copy it here. So copy paste this part over here. Okay. Now, chmod gives permissions. Okay. So we'll give it permissions to read and write and execute to here. Okay. So what does this mean? Okay, recap. Making a directory called Kaggle, copying Kaggle.json, which is this one here, over to Kaggle. We give it permissions to read, write, and execute to this whole path. Okay. And now Kaggle competitions download -c digit recognizer. Wait a minute, you can do it? Okay, there's an easier way to do it. I forgot how to do it. So you can import it without a zip file, okay? Like unzip. I think if you do that /unzip, it works. Nope. There was maybe Mandy knows. I'm not sure. You can do it without like unzipping, but yeah, let's just do it manually, okay? So we got a zip here. Digit recognizer.zip. This one is from here. Okay, we got it here. Okay, cool. Now that we have the digit recognizer, let's just the code I gave in the chat. Really? Oh, just download print path. Does this unzip the whole thing too? That's great. That's a great piece of code, huh? I'll screenshot it later. But yeah, that's good. Awesome. So let's do it the old-fashioned way. Import zip file like this. Then zip reference equals zip file dot zip file like this. Okay, capital letters. Careful there. And then go into 3 points. Copy path as a string. Paste the path here. Okay, cool. So under it, you do zip ref dot extract all where to something called content. Okay, if you don't add content here, it will go outside of this folder. It's going to be a little bit complicated to find, so slash content is in here. Okay. Now, lastly is zip ref dot close. Okay, this should work. Nice. No outputs of errors. You can see here we have sample submission, test, and train. Okay, cool. Now, we need to see the data before using it. Okay, don't use data before you check it because you don't know if the data is okay. You have to manually check it. Okay. Data equals pd.read CSV. Okay, and then we know, for example, let's get the test in this case. Okay, copy path, paste the path. Okay. Oh, no way. Here's Tammy. Hey, Tammy. Nice to see you again. Cool. Now, we have data. Okay. Let's check data.head. It gives us the first 5 elements. Okay. Check that out. So we have 784. Even if you see a 3 here, we're starting at pixel 0. Okay. So we have 784 pixels. Remember that number from here, 784 pixels, 28 by 28. Okay. We have, this is just the numeric value that's giving to each image, but this is an image. Okay. It goes from 0 to 1, and this is how it looks. This is how it looks. Okay, you can see 0 and 1s. Okay, it's an easy way to use neural networks. Okay, you just use easy images. Okay, cool. And the head gives you the first 5 values. Okay, so it means this one has, if we do data, I think it's that length. Is it? I don't remember. Oh no. It was I think it's info. If you do info, you can see we have 28,000 images. Okay, see that? Cool. Okay, now data looks good. Let's start with everything that we talked about before. Okay, we have the numbers right here, but they're in the pandas way. Okay, they're in the pandas object. We need it in numpy objects. Okay, so step 1, change to numpy. So data numpy with n equals np.array and that. Okay, could you please paste the code in the chat? Oh yeah, you can find it in my GitHub. It's right here. It's intro to NN part 1. Okay. Cool. So we have now our data as numpy arrays. Okay. Now, should I zoom in a little bit? Maybe that's helpful. Cool. So we have M and N, which are data and the shape. Okay. Width and height. Okay. And by the way, we're going to shuffle this just so it's not, in case it's ordered, like all 0s, all 1s, or 2s. Neural networks tend to get it wrong when it's like that. Let's just shuffle it, okay? So np.random.shuffle data n, okay, like this. Cool. Now, remember we needed to transpose this. Where is it? Should be here. Remember we needed to transpose this because we have it in this format. We need to transpose it here so we don't get math errors. Let's do that. Transpose, okay? So we have data train equals, by the way, are we using train? No, we're using test. Careful there, okay? I think it's recorded on YouTube. You can look for the MLH channel and you'll find it there. Okay, so let's do the same thing, but for train, not test. Okay. Same thing here. We may actually have more images here. Oh yeah, 42,000 images. Okay. Just because we need to use this data to train, and then we'll do the testing part. Okay. Cool. Data train equals data n, and we'll just get. Okay. Okay. I remember what I did here. That's it. Okay. Now we'll just get from this 1000th image all the way up to m, which is the number of images, and transpose this. Okay. Yep. Oh, thanks, Sammy. Cool. Now, where can I digit recognizer the zip? Oh, use this code right here. Make sure to have your Kaggle.json in your collab. Okay. Cool. So we transpose this. Now we need to declare our training values. Okay. Values. Let's call it values. Okay. So we do yTrain equals data train in 0. Okay. The first value, the first part is your values. Okay, which is y. Hey. Cool. Okay. So xtrain is data train from 1 all the way up to n. Okay, because the first one is the y, which is the answers. Okay, we'll get the numbers from the first one, from the second one all the way up to n. Okay, cool. Now xtrain. Oh, wait. Oh yeah, equals xtrain over 255 dot. What does this mean? Like, why are we dividing over 255? We, or neural networks, tend to love normalized numbers. Normalized numbers are numbers from 0 to 1. Okay, since we're working with RGB, then we want to make sure that every number is from 0 to 1. We know the max number of RGB is 255. So just divide it over 255 and it gives you a normalized number. Okay, it's easier for the neural network to compute. Okay, cool. Now we need, this one's not important, but this one it is. Train equals xtrain that. Okay, like this. So we'll get the amount of images that we have for training. Okay, cool. Run this. Let's see if we have no errors. We have an error. Double callable. Where? Don't fear errors. Okay, don't go and copy paste the whole thing into ChatGPT. Read it. Okay, it says mn data shape. Oh, my bad. I think it's like this. There we go. Cool. Because shape is a tuple, we cannot call tuples. Okay. Don't run away from errors. Okay. The best way to learn is to read them. Okay. Cool. Now we start with the functions. Okay. Def init params. Okay, like this. We have to initialize the parameters. Okay, the weights and the biases. Remember, weights and the biases were the B's here. Biases, weights and biases. Okay, we have to initialize them with random numbers. Okay, if you initialize them all with the same one, your neural network won't work. Okay, cool. So W1 equals to numpy.random.rand. I want you to give a number from 10,784. I'll explain what this is in a second. Minus 0.5. Okay, I want you to give me a number up until 10. Yeah, maybe. Okay, Rand, help me. I forgot what Rand did. Wait a minute. Random np.random.rand. Here it is. Let's check it out real quick. First number is uniforms from 0 to 1. Okay, 1, 2, 3. Okay, yeah. You can see 3 stands for the number of, like the first number stands for the number of lists, okay? And the second number is the amount of numbers inside the list, okay? So we're doing, I want you to give me 784, let's call them neurons, with 10 classes, okay? Minus 0.5 just in case, okay? We did the same thing for B1 equals np.random.rand, okay? We just need one number of B, okay? So we have 1 minus 0.5, okay? Same thing for W2, okay? We'll do copy paste the whole thing. So it's easier. 2, there we go. Careful here. This is the input layer. We had 784, remember? Layer 1 has 10. Okay, we have the bias. And then let's return W1, B1, W2, B2, like this. Okay, run it. It won't call the function because we didn't call it, but we know it works. Okay, 10, 1. Okay, that's good. Now we need the activation functions. Okay, ReLU, rectified linear unit. Okay, we'll get a number called Z, and just for simplicity, okay, let's leave it like, no, let's do it. Just for simplicity, we can do it like this, and I'll explain in a bit. Okay, what this function does basically is it says, hey, we'll give or return a 0 if Z is less than 0. We return Z if Z is greater than or equal to 0. Okay, makes sense? Let's see ReLU real quick. Check this out. So 0 if the number is less than 0. The number by itself if it's more than 0. Okay? Same thing here. Okay? Now, we can do, let's do if D, return Z greater than 0. Else return np that maximum between Z and 0. Okay, sorry. Okay, what's happening? Okay, everyone just calm down. Okay, chat. Remember, we need to do this. Remember this part over here? It's the derivation of ReLU, okay, which we are deactivating, so to speak, the layer. We have to do a derivation. The fanciest and easiest way to do it, you can see, hey, if you derive a number, which is x, it'll give you 1. Right? So derivation of x gives you 1. Derivation of a constant gives you 0. Right? So if our number is 0, we know, or less than 0, we know that it's a constant. So we derive it and we say, hey, it's 0. If our number is x number, we know the derivation is 1. That's the fanciest way to do it, is, hey, if our number is less than 0, should be 0. If the all number is more than 0, the return should be 1. Okay? That's what D is, okay, for derivation. The number is Z, and if we don't derive, we were just using the activation function, we just return np.maximum between Z or 0. It means give me either 0 or Z. Okay? Cool. Now, Remember, we have to one hot encode. Okay, real quick. One hot encoding. Okay, this is one hot encoding. Okay, you see we have colors. We have red, yellow, and green. Maybe this is a little bit weird. Wait a minute. Okay, cool. We have gender, male, female, male, male. Okay, we have gender, and we have two, male and female. Okay, these are two options we're given. If you have the first, or let's say the first subject, the gender is male, then the one hot encoding is 1 in male, 0 in female. If it's a female, it should be 0 in male, 1 in female. Okay, how does that look for us? Let's see if we can find the MNIST one. If not, I'll just use paint. So for us, if our number is 0, then the one hot encoding is 1, 0, 0, 3, 1, 2, 3, this number 3, 4, 5, 6, 7, 8, 9. Okay? Because we are activating 0, and all of the rest of the numbers, 1, 2, 3, 4, 5, 6, 7, 8, and 9, are not 0. That's why they're all zeros. If we had a 9 here, then the activation should be in this part over here. What's wrong? I don't know. This actually should be 0 and 1. Make sense? Because we're activating number 9, not 0, not 7. Okay, make sense? Yep. Thumbs down or questions if it doesn't make sense. Okay. So we have to create a function that one hot encodes everything. Okay. So let's do it. App just crashed on me. Wait a minute. That's one hot. Okay. We'll get a number. Let's call it n. Okay. Cool. Where's my cheat sheet? There it is. No questions. No questions. Okay. Okay. Instead of n, let's just do y. Okay. So I understood it. Oh, Tammy understands everything. Tammy, you are the best. Cool. But yeah, feel free if someone doesn't understand something, feel free to say, hey, I have no clue. And I'll try to explain it, okay? It's a lot of math in a short period of time, okay? Cool. So one hot y equals np.zeros. And we have y.size, and I'll explain in a second what this is. I see a question there. Let me just finish typing. Y.max plus 1. Okay, cool. Billy, you're the best. Thanks, Tammy. You are the best. Tammy never fails. Tammy is always at my streams. Cool. So we have one hot. We're doing, hey, I want you to give me a zeros, okay? A list or a matrix of zeros of y size times y max plus 1. I'm sorry, of y size and giving the max number plus 1. Okay? Cool. Now, one hot y np.arrange. I'll explain it after code. Wait a minute, because I don't have my neurons are not that good. Okay, so arrange y that size y equals 1. Okay, so we did the zeros. We have the number of zeros that we want. Remember that we are putting this plus 1 because we have 9 numbers, but we have 10 numbers, but the maximum number is 9. So it's 9 plus 1, which is 10, counting 0. Okay, now one hot y, we get the list and say, hey, from the list, if we activate the number 3, I want you to give me a 1 in that 3. Make sense? So we're just saying from the list of zeros, give me the number that I'm inputting here as a 1, okay? Doing this thing over here, okay? It's funky, I know, but it works, okay? It makes sense. Return 1 hot y.t. We have to transpose it, okay? If we don't, we'll get errors, okay? Because we do dot products, okay? Cool. Now we need softmax. Remember, softmax is our activation function in the last layer. Is the one that decides it gives us the outputs of in a percentage format of the classes. 90% 1, 0% 0, 0% 3, 0% 4, 2% 5, yep, so on. Okay. Softmax looks like this. This is softmax. Okay, you can see it gives us probabilities. In this case, if we were to have numbers from 0 to 1, 2, 3, 4, then the number outputted should be 1. 0, 1, 2, 3, 4. The one that has 90% is 1. Okay, this is the equation. Okay, so let's write it down. Okay, softmax, also getting a number z, a equals np.exp. exp is the e, okay, number e. We're going to elevate it to z, okay, over the sum of np.exp of z. Okay, this e to the z over the sum of e to the z. Okay, check that out. Okay, cool. Now return a, like this. Okay, cool. Next function that we need is forward propagation, or also called prediction or predict. Okay, their forward prop. Ooh, my bad. We'll get yeah, sure. It's the y size 1. Okay, yeah. So you get a list of zeros of y size in x, y max plus 1 in y. Okay, this part here, because we were saying, hey, give me the max number, which is 9, but we have 10 classes. Okay, 9 plus 1 makes 10. We have a bunch of zeros. Looks like this. 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Okay, and we're saying, hey, from this list, which is this one, I want you to give me from the size the number. So if it's for example, if our input is so remember, this is like a list of lists, okay, like this. Okay, like this. Okay, so we have a list of lists. Well, let's just copy paste the whole thing again. Like this. Okay, each one is for each image that we have. Okay, so we have image 1. Oh. Like this here, it's image 2, image 3, and we have all the way up to image I think it's 784, I think. Yeah, so we have each map maps each image. Okay, so for example, image 1 is, let's call it, maybe it's an 8. Okay, so we're saying, hey, from the coordinates of image 1, give me its value, which is 8. And in that 8, I want you to put a 1. 0, 1, 2, 3, 4, 5, 6, 7, 8. This should be a 1. Make sense? From image number 2, you get y, and maybe the y value here is 6. 1, 2, 3, 4, 5, 6. Should be this one. Okay, because this is 0. Make sense? Yes, better. Okay, and you go all the way up to 784. Yeah, yeah, that makes sense. Okay, cool, cool. I see another question there. Give me a second. I probably should use this one. There. Cool. How many prize scores? It's totally free. I don't like. It's not a course per se. Just watch it. You can just text me in on Discord. And I'll try to help if you need more help. Okay. Yeah, that makes sense. Also, cool. Okay. So we're step 3. Sorry, step 2. Forward propagation. What? No, step 3. Forward propagation. Okay. We need weights, biases, we need layers, and we need activation functions. We have everything. Let's build it. Okay, like a Lego. Okay, so we need weight, bias, weight, bias. X is your information, your image. Okay, in this case, X big or X. Is it majuscule? How do you call that? Majuscule in English. Capital letter. Yeah, there we go. Capital X is your whole data set. Okay. Cool. So Z1. What the heck Z1? Remember Z1. Okay. Is W1. We do a dot product of X plus 1. Okay. I'm sorry, plus B1 plus the bias. Okay. We do A1 equals ReLU of Z1. Okay. We're just building it. Okay. This one is the input layer. Okay. We know that it's X. See that? Here's X. This is layer 1. Okay. Z1, this part over here. We have it here. Okay. We activated the layer. Okay. Now we're going to create the second unactivated layer. Okay. Let's maybe call it like this so it's easier to understand. Layer 1. Layer 2. Okay. Layer 2, we have Z2 equals W2 dot A1. Okay. See that connection? Plus the second bias. Okay. Second bias, I said. And then A2 equals soft max of Z2. Okay. Return. Careful with the order, because the order matters when we extract the information. Okay. Careful. Z1, A1, Z2, then A2. Okay, like this. That's forward propagation. It's a linear thing. You just multiply, activate, multiply, activate. That's what it does. Okay, there's no real science there. It's just math. Okay. Cool thing is in the back propagation. Okay. Back propagation, we need Z1. Yep, remember, back propagation, we need Z1, A2, the answer, M, Z2, A1. See that? So same things that we already have here, here, and here. We have Z1, we need Z2, we need A1, we need A2, we need X, we need Y, we need W2. Okay. Now, yeah, so far so good. We need the one hot of our answer. Should be Y, like this. Okay, so we are saying, hey, Mr. One Hot encoding, give me the number in a one hot matter of your answer. Okay, so in the end, for must move, as must move's question was, so it makes more sense. prediction will look something like this. 0.1 maybe. 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, and maybe 9.9. Okay, it'll look like this. This is what softmax can output. Okay, actually, it should be. I think it should be like this in 0.99, like this. Okay, and let's call it our answer is like this, but maybe we got it wrong. Maybe it wasn't a 9, maybe it was a 0. So this should look like this. Okay, so we know that the neural network just didn't get it. Okay, it thought that the 0 was a 9 and it was actually a 0. Okay, and we'll use this one against this one, and the answer is the one that we're asking here. Make sense? I hope it makes sense. Okay, cool. I'll just get rid of this. Cool. So we get the 1 hot, and now we have dz2 equals, remember dz2? Yep, dz2 equals activated function, activated layer minus, or like answer minus the real truth. Okay, so we do a2, which we have here. Okay, minus 1 hot y. Okay, so this is layer 2. Okay, we go to layer 1. Oh, my bad. The W2, which is the weights that we want to tweak based on the error, equals 1 over m times dz2 the dot a1 the t. Okay, this whole equation is here. 1 over m times dz2 times a1t, t for transpose. Okay, cool. Now we need the bias. db2 equals 1 over m, like this. I don't like it with spaces. There we go. Times np.sum dz2. Okay, where do we get that from? Here, db. Oh, I missed db2. Oh, my bad. It's the same thing. Okay, it's like this one, but instead of dz1, it's dz2. Okay, cool, awesome. So layer 1. Okay, we're going back. Okay, from layer 2, we unactivate, we get the error. Layer 1, now we get dz1 equals w2 the dot. Okay, we want a dot product dz2. Careful, we have to transpose this one too. Okay, times ReLU with z1, but we derive it, yeah, because we're back propping. If we were forward propping, we don't derive anything. Okay, we're unactivating the activation function. Okay, now dw1 equals 1 over m times the z1 the dot x dot t. Okay, what's happening? Okay, what's going on? We went dz1, and for the weights, we need to get the previous layer. But our previous layer is our dataset. Okay, here it is. Okay, cool. Now, db1 equals 1 over m times np.sum dz1. Sound good? Okay. Maybe not, but you'll see it work. Okay. Return DW1, DB1, DW2, DB2. Okay, like this. Okay, it should run because we are not calling it, okay? Tammy knows that whenever I write code, I have to correct it like 5 times, okay? Tammy's used to it, okay? So for people who don't know me, my code always has errors, okay? We'll just tackle one by one. Okay. Now, last part is update parameters, okay? So we do def update params, which, by the way, now that I'm listening to my computer's fans, I need to clean it, change the thermal paste and everything, because it's been a year. I change it each year, so yeah. If you haven't done it to your computer, do it. If it's a Mac, don't open it, okay? Don't. It's a Mac, okay? It's not made for opening. Just pray to God it doesn't explode someday. I'm just kidding, okay? I hate MacBooks. Why? I don't know. It's just, I don't know. It's like, I don't know. I don't like them. It's like you cannot do anything with them. Like if I would like to use, I don't know, a simulator, I can't because Mac doesn't allow it. If I want to use Arduino, it has some compatibility issues. It's just a mess. I don't like Mac. I'm sorry. I've got a MacBook. Tammy, you are the exception. I love your Mac. Okay. But I just don't like it. And if you want to expand your RAM or something, it doesn't allow you to, and it's not cheap. So for that price, I want freedom. Make sense? Okay, DB1, DW2, DB2, alpha. Okay, remember alpha is our learning rate. Okay, cool. Now, is this lagging? No, it's not lagging. It's weird. Okay. Okay, W1 equals W1 minus alpha times dW1. Okay, we're updating it with the error. So if the error is too much, we update too much. If the error is too small, we don't update that much. Okay. Do the same thing for W2. Okay, I'll just show you something. If you select, for example, W1, Control D, you can have 3 cursors. See, you can change all 3 in one. Okay, and to get out of it, you just click anywhere. Okay, B1 equals. Oh, we can do the same thing. Okay, we could do this, for example. We can select W2s. If you click Control D all the way, you select everything that has to do with W2 in this cell. Okay, in this case we just want the 3, so this part over here, B1. That's cool. Yeah, should be good. And same thing, D2, like this. Okay, cool. So we return W1. Again, careful with the returning patterns. Okay, B1, W2, B2. Okay, like this. Now, we need to, oh, my bad, def get predictions. Okay, now from predictions, we need the last layer of our neural network. It's a simple thing. Return inputted argmax a2 or 0. Okay, why this? Remember, our outputs should be, imagine we have 0.5 here or 0.45, and here we have 0.55. Okay, np.argmax will take this answer, and in this case would be number 0, 1, 2, 3, 4, 5, 6. Okay, so this should be 6. But if we don't have a max, we just have zeros, then we return a 0, which makes it 0. Okay, That doesn't happen, okay? Softmax gives you a random number if you don't get anything, okay? Cool. And now, get predictions, cool. Now, we need to get the accuracy, okay? Def get accuracy, okay? Predictions and y, okay? So based on what we predicted and the real thing, we have to get the accuracy, okay? So let's just print it so we see what's happening. Okay, whenever we run it, we'll see it and return. Oh my bad. Return. NP. That sum. Double equals y over y. That's size. What are we doing here? We're getting all of the predictions that are the same as y that we actually got correct over the actual sum. So if we get 10 correct out of 100, this means 0.1, which means 10%. Make sense? So that's how the accuracy, it's 10% accurate, it's not accurate. Okay, cool. Nice. Now, real thing, real deal. Let's do it. Def gradient descent with SC x y alpha epochs. Okay, epochs are the number of iterations that the neural network will get for each for the whole data set. Okay, so we can get 10 epochs, so it looks at the data set 10 times and it studies it 10 times. Okay, the more epochs, the best. If you add a lot of epochs, you can overfit your model. Okay, overfitting means imagine blue flower. Okay, imagine this is my data set and I am teaching my neural network that this is a flower. Okay, every single flower is blue. Okay, but what happens if I give my neural network this and say, hey, is this a flower? What do you think, Chad? Is the neural network going to say this is a flower or not? The answer is it's going to say this is not a flower, right? You taught me that a flower looks blue. Okay, so because we're not diverse, or we show a lot of times, yeah, no, exactly, because the flower is blue, right? If you have a lot of epochs showing the same thing, when you give it something new, like this, I said like this, like this, it's going to say, hey, what's that? Like this is not a flower. It's a red thing that kind of looks like a flower, but it's not a flower. Okay, a lot of epochs, good. A lot of epochs, not good. You overfit. Very few epochs, you underfit. So it doesn't learn a lot. Okay, it's a process. Okay, you kind of have to see. You have a lot of functions available. You can say a function is like early stopping, where we see that it stopped learning. Whenever you can create a function that whenever you see that it stops learning, that the accuracy, instead of going up, starts to go down, then you have to stop. You say, hey, stop. Because whatever you're learning is wrong now. You're overfitting. Okay? Cool. Now, gradient descent is the, I won't say equation, it's the, I lost the word. It's the pattern. It's the name of what we're doing, which is forward, backward, forward, backward. Okay, and gradient descent allows us to descend to the minimum error, and we stay in that area. Okay, cool. So we get W1, B1, W2, B2. Okay, we get this from init params. Remember that function? Okay, real quick. Where is it? Init params, here. See that? Okay. Now, we got our initial parameters, everything in random. Okay. Now, for I in epochs, box. Okay. Cool. So we're going to iterate I amount of epochs. Yeah. And say, hey, Z1, or let's do here forward prop. Okay. Get the answer of one of the images. Okay. Then Z1, A1, Z2, A2 equals prop, or prop with W1, B1, W2, B2. Like this. And X. Okay, so far so good. We're doing for propagation in one of the epochs. Then back prop. Okay, so we get DW1, DB1, DW2, DB2 equals back prop with Z1, Z2, A1, A2, X, Y, and W2. Okay, remember back prop from here, we got these. Okay, cool. Now we get a back propagation. Oh, my bad. I don't want to text. Cool. Now we have to update the parameters. Okay. So if you see step 2, step 3, if you see init params, if you see step 1, step 2, step 3, step 4, part 1, part 2, part 3, part 4, let's call it 4 with this. See that? It's we just built it, okay? It's all the math that we did block by block, okay? Update parameters. We do W1, B1, W2, B2 equals update parameters W1, B1, W2, B2, and then we need DW1, DB1, DW, DW1, DB1, DW2, DB2, up. Okay, remember all of this is here, the params. Okay, cool. And now let's just see how it goes. Okay, because if we run this, it won't show us visually how it's doing. Okay, so let's see it. Let's see it. Okay. So if I %10, which I'll explain if you don't know what this is. So we're saying, hey, if I, let's say I is 1, okay? If you do this, I forgot how is this called, but 1, you're getting only the residue of 1/10, okay? If it's 0, this would output 0, for example. 0/10, this would output 0, this would output 0. Okay, we're dividing this number, in this case I, over 10. Basically, we're saying for each 10 epochs, I want you to print iteration I. Okay, so we're saying, hey, I want you to print iteration in the number. I want you to get a prediction. Yep. And then Get accuracy predictions Y. Okay. Now, what are we doing? For each 10, we're saying, hey, we are in the 10th, the 20th, the 30th, the 40th iteration. I'm predicting just one image using the last, let's say that using the last layer, and I'll get the accuracy from that image and the real truth. Okay, and I'll say, hey, we are maybe in error. We have 10% accuracy, which is 90% error, and we have to see it go up. The accuracy should go up to 90, 95% is really good. Okay, so return W1, B1, W2, B2. Okay, so far so good. Okay, now you'll say, hey, you don't have errors. Oh, wait, Tammy knows we haven't run anything. It has, like, we just defined the functions. We need to run them. Okay. BW1, B1. Oh, why EW? Like W1, B1, W2, B2 equals gradient descent. Okay, and then we want to do X train. Okay, we want to do Y train that we defined earlier. Okay, 0.1 as alpha and 100 epochs. Okay, ready for errors? 3, 2, 1. Yes, always. Okay, and called. Okay, again, don't run from errors. Okay, let's read them out loud. It says in line 5. Yeah, Tammy knows. Yeah, you see that, Tammy? I'll predict 5. What, like, predict, Tammy? How many errors should I get? We're 1. Okay, and chat, if you want to kind of predict the errors I'll get. Yeah, let's see how we have. Okay, for int in epochs. Oh, see that? It's for int in epochs without this. Okay, cool. Now, error again. Okay, 3. Okay, we have a 3. It's not iterable for I in epochs. Am I writing it wrong? Oh, wait a minute, it's a range. Yep, my bad. Cool. Yep. 4. Okay, Tammy says 4. Yeah, thanks so much. I don't know. My brain said no. I won't use range anymore. We have a 3 and we have a 4. Okay, 2 so far. Okay. Oh, did I run it? Yeah. Okay, it's running. Oh, there we go. Number 3. Okay. NumPy has not choose Zum with Z. My bad. Where is it? Gradient descent. It's in. Where is it? Let's just do it the easier way. Zum like this. We have 2. Where is it? Number Zum. There we go. Zum. Okay. Yep. Should run this one. Okay. Cool. Now. Okay. Now that's not good. It did 1 iteration. Oh, my bad. It's the return is out. Okay, that doesn't count as error. Okay. We have 3 so far. Okay. Okay, that should be good. Okay, iteration 0. We have. Oh, there we go. Tammy, you got it wrong. And Morgan, you got it wrong. We have 3. Yes. Okay. You can see iteration 0. Okay. 11% accuracy. Iteration 10, 14%. 20 goes 21. 30 goes 26. You can see accuracy going up. Is this? You can see that we're kind of there. Maybe we're missing some more epochs. What do you say? Let's do more epochs. Okay, 200 shouldn't hurt anyone, right? Let's see how we do. Start with 10%, 12%, 16, going up, 23, 27, 36, 43, 49, already better than before, 55 in 90, 59 in 100, 63, 66, 68, 69, 71, 72, 73. Use W2 insurance. Where? What do you mean? In what part? In the last code block? In this one? This W2? Use W2 insurance. W2 in last code block. What do you mean with that? Your username is Supravo Sengupta. What do you mean? Okay, cool. We got with 200 epochs, 75%. Not that bad. We probably could do better. Okay, 75%. It's good. Okay, for something like this, not that bad. Okay, now let's see it. Yeah, let's test it. Let's see if it actually works. Let's make predictions. Oh, my bad. I'm running out of time. Let's do it fast. X, W1, B1, W2, B2. Okay. From here, nothing. I'm just needing A2. Okay. Equals forward prop W1, B1, W2, B2. Okay, so if you see underscores in Python, it means I don't care what it is. Okay, I don't care what it is. I just care about A2. Okay, that's going to give me the answers of softmax and predictions equals get predictions of predictions. Yeah, that's good. Of A2. Oh, really? Oh, thanks, Tammy. I didn't know that. Who was the next streamer? Kari. Oh, yeah, I saw it. I saw Kari. Oh, yeah, I see it. Yep, thanks, Tammy. Thanks for the heads up. Cool. Okay, we can take our time. Okay. Cool. Now, get predictions from A2, which is the softmax. Okay. Now, return predict. Okay. We're not only getting predictions, but we're making them. Okay, based on these. Okay. Cool. Now, interesting thing. Says the predictions. Okay. So we need an index. W1. B1, W2, B2. Okay. Now, current image equals xtrain. We're going to get it from everything. Index none. Okay, like this. Prediction equals make prediction. Okay, from xtrain. It's with S. My bad. Oh, my bad. There we go. Xtrain. And I want to get it from this index and none using W1, B1, W2, B2. Okay. Now label is the correct answer. Okay. Label equals ytrain. Okay, we know that. Ytrain and index. Okay, cool. Now print. Prediction is prediction. Okay, we have our prediction here. And our ground truth with a capital L because it looks good like this. We have a label. Okay, so if we get a 2, we should hopefully see a 2 here. Okay, cool. Now we reshape current image. Reshape should be 28 by 28. Okay, dot 55. Okay, we are unnormalizing. Remember, we normalized right here. There we go. See, so if we want to plot it, we need to unnormalize it. Okay, so unnormalize image, and then plt.gray. Okay, and then plt.im show current image. Interpolation equals nearest. There we go. And then plt.show. Okay, like this. Now we'll test. I'll just copy paste this part because we have 7 minutes. Where is it? Where is it? Where is it? There we go. Let's test. W2. Oh, W2 with on capital here. My bad. DDD. There we go. Let's test index 0, 1, 2, and 3. It won't be the same as this one, okay? Because we shuffled it, and the seed of shuffling is always different, okay? Cool. Let's do it 3 to 1. Okay, got it, okay. We predicted a 9. The label is 8, and you can see it's clearly an 8. So that's one that our neural network missed. Good news. Prediction 2. Label is 2. And we can see it's actually a 2. So we're 1, 1, okay? Prediction 7. Label is 7. And this is a 7. Okay, we're 1 wrong, 2 good. Prediction 8, label 8. This is clear an 8. 3 goods, 1 bad. Yep, that's it. So let's say that we have 3 to 1. It's 75%. We got actually 75%. 75% here. See that? That's a neural network, let's say, under the hood. Okay. Now, I wanted to show TensorFlow. I didn't have time. I'll probably get it from my GitHub real quick. You can see here that TensorFlow makes everything super easy. Okay. You can see that here is a kitty. Here it is. You can see this. TF.char as layers at convolution 2D, 32 neurons, 3x3 kernel, activation equals value. See that? It's super easy. Input shape, this. This is one layer. This whole thing is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 layers. I actually ask here for accuracy. Here's a learning rate. I have a loss here. I'm compiling it. I just want to do some more things. I want to get the history, so I want to keep whatever it outputted here. This, yep, is this whole notebook. Okay, simplified here. Okay, and you can see it's running here in a beautiful way. That's what TensorFlow does. Okay, I didn't have time for TensorFlow today. You can look into TensorFlow. Let's see, TensorFlow. Do we have like? Yeah, you can click on these here. No, maybe TensorFlow, Google. I don't know. Tutorial. Maybe this one. No. Okay, cool. So I have another idea. 0 to Mastery Academy TensorFlow. So I learned TensorFlow thanks to 0 to Master. Okay, This is the Udemy course that I used. It's not $125. It's Mexican pesos. It's like $5, $6-ish. Okay, really good. I learned a lot. Okay, Zero to Mastery. Shout out to them. They're really good. The only bad thing is they don't explain that much under the hood what's happening, and not like this. Okay, so now that you learn this, you can go and learn TensorFlow. When you get the errors, because you'll get a lot of errors, don't ChatGPT them. Kind of understand what's happening, because the problem is not your code, is your math. Okay, sound good? Ooh, no lights. Wait a minute. Let's do magic 3, 2, 1. There we go. Lights. Yep. Okay. Sound good? Cool. Now, please, 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 just in case you got in a little bit late, register here. And I want you to give me feedback, okay? Wait a minute, there we go. Cool. Now, I appreciate the good comments, okay? I don't take personal the bad feedback, okay? If you say, I didn't like Bully's stream, I won't take it personal, okay? It helps me grow, okay? So how does this look? If you go here, you'll see the feedback. Continue here, and then you'll type intro, what? And neural networks. Here it is. Building an NN from scratch. Click on this one. And then how do you rate the contents of the building of neural network scratch? If you didn't really like it, you can put a 1 or a 10 if you really liked it. Okay? I don't take anything personal. I want to grow and I want to be better, and that's thanks to your comments, okay, and your feedback. Okay, Tammy, thank you so much for always watching my streams. I really appreciate it. And yeah, I think that's it for today. Again, just in case, here's my GitHub with today's stream and tomorrow's 2 streams. Okay, tomorrow we have building a very, very smart IoT device. So if you wanna learn a little bit about IoT, MQTT, electronics, and AI, tomorrow at 5 p.m. EST. Yep. Cool. Awesome. Thank you so much. I'll just remove this part over here. Thank you so much. I appreciate that you stayed in the stream. I'll see you around. Okay. I think the next stream was canceled. So in 2 hours, you have MongoDB vector database with Alberto. Alberto's really good. Okay. So please, if you want to join him, okay? Cool. Have a nice day. Thank you so much. And yeah, I'll see you around. I hope to see you tomorrow, okay? Tammy, see you tomorrow. I know you'll be there. Bye-bye.